All right, welcome. So in this video, I want to start talking a little bit about analyzing our algorithms. The last couple of videos we were looking at proving them correct. Now I want to count some of the operations that they take. And so we're going to start with the same algorithm that we were looking at previously in an earlier video, a couple of videos ago, the minimum algorithm. And again, maybe take a look back at one of the earlier ones if you want to review the algorithm, although it's a fairly simple one. Where we just iterate through the elements of our list and we, update a minimum so far. That's what we use to prove that it was correct. And then at the end, we return that minimum so far. It should be the minimum of the whole list. We already went through the steps necessary to prove that correct. So now that we know it's correct, we might want to answer a few other questions related to this. In particular, the one that I have sort of highlighted here is how many operations does this take? Now, the way that I've stated it here, how many operations does this algorithm take? Question mark is sort of a vague version of that question, and the more experience you get with algorithms and computer science, the more you're going to look at that and say, well, that question begs a couple questions. One is, I've got a couple listed here. One is going to be, well, what actually do you mean? What counts as an operation? And I'll mention in a second that there's a couple different maybe resolutions at which we can count operations. Sometimes there's only going to be one operation that we're concerned with, like an assignment. Other times we might want to count every single operation that might count. Okay. Other question that might arise, again, if you have a little experience with this, you might realize that, well, this algorithm is stated very generally for any list A. Well, we can see this list A has a size of n. Well, what is that size? What is that n? Is going to change, for instance, how many iterations of this loop we're going to have. So the runtime, how many operations this takes for this algorithm to complete is dependent on the size of the input. And that's a pretty common thing for us to do in computer science, is to say, of course, well, maybe not always, but for a lot of algorithms, if you have a larger input, you're usually going to have to take more time, and sometimes also take more memory or space to store your solution or to store the working memory that you use while you're constructing your solution. So because of this observation that the larger the input, usually the more time and the more resources in general that you're going to need to take, it means that when we start answering the question, how many operations does this algorithm take, that answer is rarely going to be numerical in the sense of 20. It's going to instead usually be a function of n. So as n gets bigger, maybe we spend 5n time carrying out this algorithm. Well, we'll take a closer look at that as well. And then the last question that I want to maybe highlight here when counting algorithms is that so we sort of highlighted that this loop is important because however many times we do it, that n is important. But the other thing that's important here is this branch. So this if-then is a branch where we make a decision. And sometimes when we make a branch, we're going to go into one body of operations or another. And so, of course, here, the question that I've just raised is, well, how do we handle that? Well, let's take a closer look at these questions then. So as I mentioned, let's look at the first one. Well, what counts as an operation? So I usually describe this as what I call the resolution of our analysis. And so you might already be familiar with this idea of a resolution. You can think of sort of a fine or a rough resolution, high level or low levels. Sometimes these words can be a little bit confusing, but basically the way that I think of it is maybe we can either be zoomed very far out, looking at sort of a bird's eye view where maybe only one operation is all that matters to us. It's only one that stands out. Or we might zoom our way all the way in where we can see every single detail, every single operation, and that might be a very fine level. We might be looking at that. Now, the idea here is what kind of operations are important to the analysis that we are currently undertaking. Now, sometimes we might be and analyzing, say, the multiplication algorithm is one that comes to mind. In the multiplication algorithm, we're multiplying two integers together, for instance. Let's make it simple with two integers. Then to do that, probably the larger the integers are, the more operations we're going to take. Well, specifically then, we're down counting what I'll call bit operations. We're counting every time we compare two bits and add them together or multiply them together. Now, more commonly in analysis, we don't go that deep into the analysis, into that many details. We usually try and abstract away some of those bit operations, in the sense that you've probably had some advice given to you maybe on other times that just simply adding two numbers together, if you have two variables, an x and a y, and you do a simple arithmetic operation like x plus y, usually we'll say that that's just one operation. We don't go all the way down to the bit details there and say, well, how many bits are in these numbers and how many bit flips do we need to do there? And we're not counting each one of those operations. We sort of lump them all together and just count them all as one. Now, what that means is we're abstracting some details away, and like I mentioned, that sometimes we might even abstract away those arithmetic details and say, well, all that I'm going to be focusing on is an assignment. Now, I find that most of the analysis that we end up doing as computer scientists on a day-to-day basis, it lives in the middle realm here. Usually we're not so far up that we only care about how many assignments we do. And usually we're not so far deep and down that we care about the bit flips that are going on. Instead, often we're in the realm of, say, a JavaScript or a Java program where, yeah, we'll probably count arithmetic operations like x plus y minus z and so on as constant time operations. Whereas we will, we won't worry about the bits all the way down, but we'll probably count all those operations. We will focus on them. We won't just sweep all of them under the rug. And so that puts us sort of in what I would count as the mid-level resolution. And that's where I'm going to go with our analysis here. Part of the reason we're going to live in the mid-level here while analyzing algorithms is if we don't actually implement in some implementation level, there are no details for us to go down and dig into. So for instance, I was talking about bit flips. If I don't actually go and tell you how I'm adding two numbers together or multiplying two numbers together, you're not going to actually be able to go down and analyze those details. So often we might need to know, say, what language are we in? And then maybe if we are even in that language, well, which tools within that language are we using to, say, carry out this multiplication? There are different ways to carry out multiplication, even of two very simple numbers like 2 times 2. So those details, I don't want to get bogged down in them, and that's usually one of the reasons why we don't go into that very high detailed analysis. We'll stay in this middle realm. So here I said what common operations we might count. So a declaration might count, an assignment might count. So notice those are sort of, I count those as sort of two different things. For my simplicity, I usually am going to just sort of say declarations are kind of for free, but that depends. That's sort of one of those programming language details that you might know. The compiler might actually take 2 steps to do this instead of 1. Usually for most of our purposes, the difference between 2 steps and 1 is not going to make a big difference. So it doesn't really matter how you count these two. Now, like I said, I usually say declarations are for free, but an assignment, so what I'm talking about is something like this. Is this let m equal a? Is that a declaration and an assignment, or just an assignment? I'm just going to call it an assignment. A comparison is something like this. Is ai less than m? That usually takes a step. Output, so that's maybe like a return or a print statement. Sometimes those take a lot of time, maybe not just one step. Logical and arithmetic operators, that's what I was talking about earlier, about maybe an x plus a y minus a z, or we don't really have any up here, although there's one hidden inside this for loop. Logical operators, well, this less than isn't really a logical operator, but the statement that is created here is a logical expression, and we could say join that to another one with an or an and, or negate it with a not. All of those are logical operators. Those are operations we should count. And then method calls. Well, here I'm going to assume this is a method or a procedure that we're calling, and so entering it we'll assume is going to take an operation. So we can actually go through and maybe count those operations if we like. And so I'm going to go ahead and do that and say, well, how many operations are there on each of these lines? And starting with that first line here, I'll say, well, that's a method call. Some of us might dig down a little bit into the details and say, well, what about passing in the arguments here? Does that take time? What's going on there? Now I'm gonna for the moment say that that's all going to be one operation, but you might know that in some languages that might mean setting up some number of references for each of the arguments. Although I'm not going to try and get down into those deep details. I'm going to say the entering into this method, I'm going to say is one operation. I'll call it one method call. Now on the next line here, as I mentioned already, I'm going to call that one assignment, and I'm not going to worry about declarations in at least my math. Now you can imagine someone else might like declarations, call them one and say this is a declaration, in which case they might call this two operations. If they do, they're going to have, at least for this line, one more operation than I am. And again, as I mentioned, the difference between 1 and 2 is usually not going to make a big difference at the end of the day. And we'll see that, maybe not in this video, but after a handful of videos, we will be well prepared to see why that difference between 1 and 2 operations isn't really that important. What about this next line here? Now this is a very tricky line, and it's actually, we're going to luckily go through a few good examples of this so we can sort of put it together. But sometimes what's helpful here is for us to actually think about a implementation, and a very common syntax for a for loop is the C syntax or the Java syntax or JavaScript. I'll use similar syntax, where we have these sort of three components of the for loop. We have the first bit, which is usually actually a declaration and an assignment. Let's say we have a for, in this case it would be I equals 2 would be the first one, and that would be sort of the declaration. That's the first step. When you enter the for loop, you have to set up your counter. Okay, now I'm going to call that an assignment, but let's think for a second and consider what that syntax also has inside it. What else that syntax has, what's next, is a comparison. That comparison is technically, we think of it as sort of the component of the while loop, while this is happening, right? Something usually like while I is less than 10, right? We've got some sort of statement that is going to be used in the for loop to determine when we terminate the for loop. Now that's one comparison. And then the third component of the for loop syntax, and again normal C syntax and so on, is, well, we'll often throw in the I++ or something. Now I call it the increment here. And in this simple for loop structure that I've got here, that's exactly what is implied. When you say in pseudocode for I equals 2 to n, we assume that means 2, 3, 4, 5 up to n. We're doing a plus plus in this type of structure. So how do those operations operate? How do we count them when we want to start counting how many operations are carried out by the for loop? Now that's something that you may not have got down into those details when you talked about for loops, when you learned about how they work. You just realize you need these different components. Well, logically we can sort of piece it together. Like I said, that first bit, the declaration, the assignment, that comes the first time we enter the for loop. Okay, I equals 2. So let's imagine the first time we came through here for a moment. For a moment, let's think n is big, okay, at least bigger than 2. So the first time we come in here, we hit this line, it goes I equals 2, let's count that. I'm counting that as 1, that's one assignment. But we also need to remember that the next thing we actually do before we enter the loop, this is not a do while, for loops are while loops, which means the very first thing we do is check our condition. Is 2 less than or equal to n? If it is, then we can iterate. If it isn't, then that means we're done iterating, we need to go. So remember, if our n was say 1, that would trigger us an exit. We're done, we are already out, we don't enter at all. Okay, but in this case I said let's imagine our n is big. So we would do our assignment 1, I equals 2, and then we would check, is I less than or equal to n? Yes, it is. So that's a second check. That's a second, that would be our comparison now. And then we enter the loop. Okay, so let's look at this line here. Now this line, inside this loop, oh, sorry. Let's go back and add what I had here. So I said one assignment here. That was the I equals 2, and then one comparison. Now, why do I have here one assignment or increment? Well, what I'm saying is, say we came back around and we hit this line again. The next time we hit the line, the first time we hit it, we did the assignment I equals 2, but the next time we hit this line, we do that third component of the for loop syntax, which is I plus plus. That's an increment. And then after the increment, again, we do the comparison. So my comment here is saying that every time we hit this line, we actually end up doing two operations. The first time it's an assignment and a comparison, and each time after that is an increment and a comparison. So every time we hit this line, it's 2, even though it changes from the first time to every other time. Okay, now down to this line. Now what can we say about this line? So this line is also sort of like the hidden line up here. It has a comparison, so we know we're doing one comparison on this line. And then this is one of those branches that I mentioned in the previous, in the earlier slide, which is when we do a branch, sometimes we're going to either do the then branch, the then body, or the else body. This doesn't even have an else body. So in this case, the then body has this operation, which is one assignment. The else body, so if this isn't true, the else body has 0 operations in it. So what that means is on this line, we're either going to do one operation, the comparison, and then hit the else, which has nothing in it, or we do two operations. We do the comparison and then we do the then branch, which has this assignment in it. So this line technically has one or two operations on it. So again, I've put this here as one comparison plus, thrown in brackets here, possibly one assignment. And I'm going to leave for the moment, just say, well, what do we do with that possibly? Well, I'll leave that for later. Okay. Now, next. The next line here, the end for. Now, technically, this is a closed bracket. This is an end scope. Sometimes we think this is just a non-operation. And when you throw a closed bracket on your scope identifier, say in Java or again JavaScript, you don't have an operation there. That's just an indicator to the compiler or to the reader that, hey, this is the end of the scope here. So we might treat it as that. However, what actually happens when we exit the for loop is we go back and we hit this line one more time. And so I'm going to count those operations here. What do I mean by we hit this line one more time? I mean, say we just finished this line for iteration n, right? Then what happens is we don't immediately exit. We actually go back here. We do I++, so we went from I equals n to I equals n plus 1, and then we compare I to n, and we do the comparison one more time, and we find that we failed. Then we exit. So we actually do the one increment and the one comparison one more time. So I'm actually going to, I usually, when I'm doing this type of analysis of my algorithms, where I'm counting every operation and trying to get every one, I will include that on this closing for the loops, whatever the cost of exiting the loop is. So the cost of exiting this loop is 2 more operations. Okay, so again, what operations are they? We go back up here, we increment I one last time, we find that we've gone past the end of n, and that's when we branch out and we exit. Okay, that leaves us with the last line. I call that one, that's our output, that's our return statement. We send it back. So if I'm counting, the call to be 1 coming in, I count the return going back also as 1. So that's sort of a good line by line analysis. Now the problem with this, or maybe not the problem, but the thing that has been left out, is that we've only done a line by line, and we've forgotten that this for loop is going to go over and over and over again. We've figured out how many operations are carried out each time we hit these lines, but we haven't yet accounted for the fact that some of these lines, these two in particular, we're going to hit more than once. Now, this one will probably only do once. This one will only do once, but these two we could do some number of times, dependent on n, it looks like. Okay, so let's push this analysis a little bit further. Okay, so now what I'm going to do is I said that we made this assumption, or rather the number of the times that we're going to execute these lines depends on n. So why don't we go ahead and fix n? Why don't we pick an n and explore, at least for the moment, what changing n does to the number of operations. So let's start with the simplest case, n equals 1. Okay, remember I mentioned in an earlier video, n equals 0 doesn't really make sense for the minimum problem. So let's start with n equals 1 and see what happens. So when n equals 1, let's see if we can count. We do this first line, yeah, we count that. We do the assignment as well. But when we get to this for loop, we need to be careful here. We actually immediately exit. Okay, let's make sure that's true. When n equals 1, we'll set I equals 2. Well, 2 is greater than 1, so we do the assignment and we do the comparison, but then we exit. So we don't actually carry out this line. And we don't double up. We don't actually do this exit cost. This exit cost is all we do. So we actually only do these two operations and then this final operation as well. So let's count them all together. We got 1 to come in. We have 1 here. We have 2 to handle the loop, even though we don't actually go in it. We just immediately exit. And then 1 more. So that was 1, 2, 3, 4, 5 operations. So again, let's just make sure. 1 call, 2 assignments. The assignment here, the assignment to start out the for loop, the comparison in the for loop that makes us exit, and then we return 5 operations. Okay, what about the next value of n then? Let's try n equals 2. Okay, so again, looks like we'll still do the method call, yeah. We'll still do our initial assignment, yeah, and then we'll hit this for loop. Now, when we do this, we're going to set I equals 2. Since n is equal to 2, the comparison we do is I less than or equal to n? It is, so we actually enter the loop in this case. Okay, so far we do 1, 2, 3, 4 to enter the loop. Then we get to this one here, and we do this comparison. And as we mentioned before, this line here is either going to hit us with 1 or 2. So it's here where I'm going to introduce us with sort of another way that the operations might depend. The operations, as we already saw, might depend on n, the input size, but the number of operations might also depend on specifically the input, how the input is set up. Some inputs are going to be easier in the sense that they take fewer operations, and some are going to be harder in the sense that they take more operations. And so when this is the case for our problem, we usually characterize some inputs that are the easier ones. We might call one the best case, the one that is the easiest, the one that takes the fewest operations. And then we might also consider the worst case, the one which is the one that takes the most operations. And usually we're interested in the worst case because, well, we plan and prepare for the worst case. So in this case here, let's see if we can check these two cases. The best case here is we do our comparison, but we don't need to update our minimum. The minimum so far is already the minimum. In that case, we skip this extra operation. We only do 1 operation here. In the worst case, though, we do have to update our minimum. And we can think here ahead a little bit. The absolute worst case is if we had to do that every single time. Okay, every time we had to get, the minimum kept getting smaller and smaller. What would that mean? That would mean A1 had to be greater than A2, is greater than A3, and so on. So if this was already in descending order, meaning the last one was the minimum and they kept getting smaller and smaller, then that would be the absolute worst case where every single time we hit this comparison and we have to do the reassignment. So we sometimes call that the worst case. Now we were only looking about one iteration of this line, meaning what was the worst case? Well, we saw the worst case of this line is we do 2 operations instead of the best case where we did 1. Okay. All right, well, when n was equal to 2, when we hit this next line here where we're supposed to iterate back up, we're actually going to exit, because now when we increment I to 3 and 3 is greater than 2, we exit. So we will do 2 operations here to exit and then 1 more to exit the method or return the value. So let's go through and count them together, and again, conscious of best case versus worst case here. So we did 1, 2 to enter. It looks like that's the same. Okay. Now 2 to enter the loop, so we're up to 4 now. Now this line, if we carry it out in the best case, we do 1 iteration, that brings us up to 5. And if we do 2, then that brings us up to 6. So 5 or 6, best case, worst case. With another 3 to exit it, looks like we have 8 or 9 as our best and worst case. And so here I have the best case for 8 operations and the worst case for 9 operations. And as I've mentioned, in worst case analysis, we usually assume that we're carrying out the more costly of the 2 branches. So this usually occurs when we have an if-then branch like we have here. So we can see after our analysis here that at least for n equals 1 and 2, that the actual number of operations carried out by our algorithm, of course, changes as n gets bigger. But it also depends on ultimately which branch we take, which depends on our input. And so we call this the best or the worst case. Now again, typically we're going to focus in on worst case analysis, meaning we're not always going to have competing analyses. Well, we will, but we'll just privilege one over the other. So whenever we make a choice, you know, are we going to go down this branch or the other? We're going to usually favor the worst case analysis, saying, well, which branch is worse? That's the one we'll go down. Okay, so how do we deal with this? I think I mentioned this to get us started, that the expression of the runtime, or the number of operations carried out by our algorithm, we're going to use a function of the input size instead of a numerical value. So I thought it was probably worthwhile to revisit or review what a function is in a mathematical sense, in a formal sense. So if you remember from some of maybe your other math classes or other studies, a function then we sometimes call it a mapping between 2 sets. So now that we've got a little set theory under our belt, we can maybe more appropriately say what a set is. And the 2 sets we usually call the domain and the codomain, sometimes also the domain and the range. The domain being what we are mapping from, and the codomain, or sometimes also called the range, although those terms have slightly different meanings, is what we are mapping to. Okay, the set we are mapping to. And so our function is going to take elements of our domain, the set D, and turn them into elements of our set R. So here we've got that sort of denoted as F takes as an input a D, and it spits out an R, where D is something from the set D, and R is something from the set R. And we also use this other sort of notation here to sort of express what I've got worded here a little bit more verbosely, which is here this is just saying F is a function that maps from this set D to this set R. And that's sort of the formal way to do it, but most of our functions are going to be on sets that we already know, sets like the naturals and the integers. So here I've sort of got a different kind of function. This is a Java function where we have sort of an integer return type. It takes an integer as an input, and here what we're sort of saying is those int values here are basically like naming our set D and R to be the set of ints in Java. Okay, so this function takes as input, like F does here, an int, and it gives as an output some other potential int. In this case it squares it. This is the square function. So we might say that this function maps from the integers to the integers. It takes an integer as an input, and it outputs an integer as its output. And so we might write that as this. So this code carries out or implements this mathematical function that maps from the integers to the integers. And I've just got a little note here that we can be slightly more precise, that in squaring, the output's always positive. In Java, that we don't distinguish between ints and natural numbers, but in math we do. So we could indeed write this slightly differently and say that this function actually maps from the integers. You could take any integer, but it only gives you natural numbers back out. Just another way to sort of apply this notation to sort of reflect on the type of functions that we might encounter. Now, why are we introducing functions here? Because we want functions to stand in for runtime expressions of the runtime of an algorithm, which we'll usually call runtime functions. And so those functions, again, are going to map from one domain to another. Well, the functions that we're interested in, we usually call, like I said, runtime functions. At least the way I'm going to characterize them right now is I'm going to characterize them as functions from natural numbers to natural numbers. And this usually makes sense for the following reason. The input to the function for a runtime function is supposed to be the size of the input. The size of the input, at least for the inputs that we've considered, and almost all of the standard inputs are going to have what we call a discrete size, which means that that size can be expressed as a natural number. So we consider inputs of size 1 and 2, but we don't consider inputs of size 1.5 or pi. Those aren't meaningful sizes, okay? And so that's the input part here, natural numbers. Then what about the output of natural numbers? The output of natural numbers, the reason we assume that is because the output is supposed to express a number of operations. And again, we might have 1 operation, 2 operations, 3 operations, but we don't have pi operations or half of an operation. Those don't exist. And so we should assume the output is also natural numbers. Now, we're sometimes sloppy about the output side. And actually, we're sometimes sloppy about the input side too. We'll sometimes blur these into the realm of the reals, or at least rationals. And we'll usually stick to the positive ones, but we'll sometimes blend into those ones. Just because maybe we're a little bit lazy. And what I mean by that is sometimes we'll use a function like, let's say, log n. Now log n, most of the times when you plug in integers for n, you'll get non-integers out. So that means we might have a function here, log n, that maps from natural numbers, say, to not natural numbers, real numbers. Well, what we do there, if we want to turn them back into natural numbers, is we usually apply one of the very simple rounding functions like floor or ceiling. That will just take that rational number or irrational number and turn it into a natural number for us. And so the reason I say we're sometimes sloppy is we'll forget to put the ceiling function in there or the floor. Just because it's a little bit of extra keystrokes or a little bit of extra notation on a whiteboard, and so we'll just leave it out. And usually also because that extra little bit doesn't carry a lot of extra information for us. We understand that usually we mean a number of operations as a natural number, and so if you tell me that it's 3.5, I know you probably mean 4. And so we'll sometimes just ignore that. We're a little sloppy on that end. But every once in a while, we might grab a function, and it's worthwhile for us to remember that we are only usually plugging in natural numbers into it. And that means we have a little freedom of which functions that we get to pick. Okay, so that's a little bit of a discussion about what a runtime function is. It's different than a normal function, and we don't really have a formal definition. I've set it up here as formal, but this is still a very vague description of what a runtime function is. I'm really only saying that it expresses the number of operations, whatever that means. That's where we need to fill it in. This is where the vagueness comes in, okay? And as I mentioned, we're sometimes sloppy on this end. Well, as it turns out, not all mathematical functions that you may have encountered are good examples or good candidates for a runtime function. Our runtime functions, because they have this format that they typically represent input sizes and numbers of operations, there's more that we can consider about them. One is that since it's representing a number of operations, we typically don't have negative operations, okay? think of what that might mean. So an algorithm takes a -5 operations, meaning you got the output before you even asked for the answer, before you ever called the method. That, of course, is something that doesn't represent how information processing works in the natural world, maybe in a magical world, but not in this one. And so we do not have runtime functions that have negative values. So that means we don't want to map into the negative range of the integers, only into positive ones. And so here I've got sort of two definitions of what it means for a function to be positive. We will say a function is positive if it only maps to positive numbers. And then we have a slightly different definition, and this is the one that we actually usually apply, which is non-negative, that a function is non-negative if it is greater than or equal to 0. And sometimes we permit 0 operations. That makes sense. -1 operations doesn't, but 0 operations does. So we'll sometimes allow 0. And so usually what that means is our runtime functions, the ones that we are typically going to rely on, must be positive, or maybe more precisely non-negative functions. Now, following the same idea, that is borrowing the idea of what are these runtime functions supposed to represent, they're supposed to represent functions, number of operations for an algorithm. We also mentioned that typically as the input size gets bigger, so does the number of operations. So as the n that we put in gets bigger, so does the n that comes out. And this, if this is a property that's true of your function, we'll usually say that this is a increasing function. So in this case, I've got stated strictly here, if a function is increasing, if and only if f of n is less than f of n plus 1 for all values of n here. And what this means is that as we iterate through the values of our f of n, it keeps getting larger and larger. This is what we will call an increasing function. Again, just like the same principle above for positivity versus non-negativity, we might sometimes permit functions that don't grow at all. We just don't want them to shrink. That's the part that doesn't really make sense. So we might permit a non-decreasing function, which is one that is less than or equal to. It might be equal to the next one, but never shrinks when we get to f of n plus 1. So what we have here is, again, two sort of rules of thumb, that any function that's meant to represent the runtime of an algorithm should probably be a non-negative function and should probably be a non-decreasing function. And here I say probably, and I'm sort of waving my hands a little bit still, because some functions are still good, good runtime functions, but maybe violate these conditions in certain occasions. So my example might be, well, I've got two examples here. Let's start with n, just the function n, okay, f of n equals n. All right, so say this is our function n. Now notice here, the way I've drawn it, it is indeed increasing, and it is indeed above our 0 positive. But what we might notice is that if we kept drawing it out this way, it is indeed negative before we get to the point 0. Now, this part actually is not really a problem for us. Now, why not? Because remember, our input to the function, if this is let's write this as f of n equals n, this is the input. When we put in our n here, we usually only put in positive n's because this is the input size, right? So it's not a bothersome, or it's not a problem for us that this function happens to be negative before we reach 0, okay? That's actually not a problem for us. And let's look at another one, which is here. Maybe I'll draw, again, it's over on this side here. Whoop, that's a really bad version. Blur your eyes with me for a second and imagine I drew an n squared, okay? Definitely not n squared, but let's imagine it is. The purpose of drawing this one is that indeed it is decreasing on this portion as well in the negatives. And again, this does not eliminate it as a good runtime function just because it's decreasing on this range. And in fact, what is important to us more, that it is increasing and positive as we approach infinity, as n gets big. Okay, for small values of n or negative values of n, we don't really mind. But for as n gets large, we're looking for functions that are increasing and are positive, or non-decreasing and non-negative is technically the rules we're looking for. So that's what we see here. And so what that means is it eliminates some functions from our candidates of runtime functions. Specifically, again, if you've been studying functions a lot in a calculus sort of context, then the functions that you might not need to consider as much are the trigonometric ones. So your sine, your cosine, and your tan. Again, some of those oscillate or go to infinity and so on. These weird properties are not actually good properties, or not the properties of a good runtime function. So all those functions we can sort of push to the side for the purposes of computer science and analysis of algorithms. But the functions that come to the forefront then are polynomials, which we have a lot of experience with no matter what you study usually, but also logarithms and exponentials. And so those are the ones that we're going to have to maybe brush up on if it's been a few years since we took a look at them. Let's take a look at sort of a final question that I want to address in this video related to this algorithm, which is how can we answer a simple question, which is how many assignment operations does this algorithm use? So this is a very high level analysis, very rough analysis where we're not going to be looking at very many details. We've decided the only operation we care about are assignments, and we actually can see here that we actually only make assignments in a couple locations. We make one assignment here, we make one assignment here. These are non-negotiable assignments. We make them no matter what. And then there are these assignments here, the ones we might make or not. Okay, how many of these might we make? Okay, so here I want to make this argument that we can make this pretty easily. Let's go for the worst case argument here. So let's assume that every time we have to make this assignment, how many would we make? Well, the answer to that depends on how many iterations there are, how many times we go through this loop. And we can see here that by starting, if we started at 1 and went to n, I think most of us can see quite easily that would be n iterations. But starting at 2 means we have n minus 1 iterations. So I'm going to do a little bit of math here. So actually, it looks like we got a bit ahead of ourselves. So we have 2 assignments before the loop. Okay. So the next bit is we're going to say that there's going to be n minus 1 assignments carried out in the loop in the worst case, remember, so we're assuming every time we have to do this. It will only happen for some inputs, but that's the worst case. So if we put that all together, we could say that we had our function, our runtime function is going to be 2 plus the n minus 1 from the loop, which gives us n plus 1 assignment operations in the worst case. Now remember here, we're only counting assignment operations, not all of the operations like we were looking at earlier. I'll save that for the next video. And so that actually makes it a little easier on us to do the analysis. We sort of skipped over a step because this was a pretty easy one to analyze by saying, well, of course, there's n minus 1 iterations, and that means one assignment per iteration means n minus 1 assignments. That's a pretty straightforward and easy argument to follow. However, sometimes our loops are a little bit more, you have a little bit more operations going on in them than this, or maybe we want to have a more fine analysis where we're not just counting assignment operations. Then what we're going to use is we're going to use a summation to express the runtime of this loop or of other looping structures as well. And so what I'm going to do in the next video, I'm going to save it for the next video, is we're going to come back and we're going to look at how we can use a summation to express the runtime of a loop, and then maybe do a finer analysis of this same algorithm here. All right, I'm going to leave it at that. So thanks a lot for watching, and we'll see you again in the next video.